in the stellar interior. Passes out through the surface, passes out through the surface of oops, of the stellar atmosphere. As a constant flux of energy, as a constant flux of energy. Okay, I guess this is quite, that paragraph should make sense. That's a pretty straightforward statement, which means the flux F is independent of depth. Remember, flux is the energy per, well, it's the intensity per unit area. So it should be constant throughout the, if all the energy that is produced inside the star is coming out, that means the flux should not depend on the depth of the atmosphere. All right, so what this means is that this would be 0. Okay. Now, from equation number 54, then we can say that J is equal to S. Okay, the average intensity would be equal to source function. Call this equation number 56. Just for the purpose of refreshing our memory, this is the average intensity. Sorry, the average specific intensity. And this would be the source function. And this particular equation, or this particular relationship between G and S, is called the condition of radiative equilibrium. Okay. Right, so we're going to go further in our algebra using equation 53a and d6. '51 becomes mu over I over tau. I is a function of tau and mu would be equal to I minus of prime. Okay. So anyway, my advice is that you should not just skip these steps of algebra. Okay, you have to try it yourself and see what's going on. Anyway, so this equation can be solved exactly. This can be Let me write it down. This can be solved exactly for I, right? Let's see. For I is the function of Tor and me. So, but we're not going to do it right now. Because that would be kind of a headache. Okay. I mean, solving it exactly. But instead, we're just going to discuss about an approximate method for solving this equation. Okay. Right. So this is a much simpler way of solving it. Should I write it down? Maybe. An approximate method of solving this equation. Okay, that's what we're going to. This equation in the sense for I. Right. Now, as we've already established for radiative equilibrium, that means whatever the energy is produced inside the star is coming out of the surface, coming through the surface. So we've already discussed this condition. F would be constant with respect to optical depth, or the depth of the atmosphere. Then can integrate the equation number 55. Integration of equation 55 would give you radiation pressure equals F over C plus Q. Now Q is a constant. Anyway, let's call this equation number 8. This is Q. Rewrite it. Q. So this Q comes from integration. It's just a constant of integration. Okay, it has no real meaning right now. It's just some arbitrary constant. Maybe I should write it. Is constant of integration. Okay. And also in previous lectures, we have, let's say from previous lectures, you can write down that radiation pressure would be 1/3 of energy density. And this is true for isotropic radiation. So, okay, we'll keep it, we'll keep that equation for the moment. Let's call this equation number 50. What number would it be? 59. Okay. Now you had to go back to equation number, let's see, 50. Yeah, just go back to equation number 50. Okay. I mentioned that before, but let me just repeat it. As we go deeper below the surface. The anisotropic term becomes negligible, right? That if we already know this, becomes negligible. And this implied that you're going to have isotropic radiation, right? So in this case, equation 59 is valid. Okay, so equation 59 is valid for isotropic radiation since we have isotropic radiation. From equation number 50, we have isotropic radiation deep below the surface. We can use equation number 59. So that's what I'm writing down here. 59 is valid for this case. But, so this is deep inside the atmosphere, deep down, deep below the surface, okay? Right, but this would not be valid. I mean, the equation 59 would not be valid just below the surface. Not valid. Because just below the surface, it's not going to be isotropic radiation. Okay, according to equation number 50. However, if we are to assume the equation 59 to hold everywhere, then it is known as Eddington approximation. Eddington approximation. Okay, so let me just summarize what I just said in this last paragraph. Apparently, we can use equation 59 deep below the surface because the deep below the surface, you just have isotropic radiation according to equation 50. But just below the surface, it's not going to be isotropic radiation. So you can't, which means that equation 59 is not going to be valid straight away. But if we are to assume that the equation 59 is valid everywhere inside the atmosphere, then that case or that condition is called the Eddington approximation. Okay, so we can assume it is valid under a certain approximation. And that approximation is called Eddington approximation. Okay, I hope that is clear. Right, which allows us to write another equation. We're going to combine equations, these equations. (52), 56, 58. 58 and 59. We can write force function S equivalent to 3F by 4 pi times 4 plus Q. For this equation number 60. Okay. Now, we're going back to equation number 51. Okay, the actual equation that we are trying to, in a way, we're trying to solve, but really, anyway. So if you go back to equation number 51, you can write the solution to equation number 51 as, okay, let me write solution to equation 51 can be written as, this is the sort of the general solution. It's a solution for I, the intensity. This is, we're going to write it in, let me see. Yeah, I'm just going to write it in for mu greater than 0. Okay. Solution is going to look like something like this. It's O mu B, and we call this equation number 1. And if the radiation is coming out of the surface, and not if the radiation coming out, but for radiation coming out, out of the surface, we have discussed this condition before. This would be 0. Okay. Please refer to that place where we discussed that. Then the solution becomes, okay, so this is for radiation coming out of the surface, right? Okay, so the total is going to be 0. It's going to stay there, and you can get a simpler solution like this. Okay, just to have total is equal to 0. That's what I mean. Right.